Okay, let me talk for a second quickly about this square root factor at the bottom. It's a very common factor that we see through a lot of relativity. So this factor of 1 divided by the square root of 1 minus v squared over c squared, we're just going to give that a relativistic um, a variable name, and it would be the relativistic constant or something to that effect. And so we're going to use the Greek letter gamma to explain that. So in that case, so using this, our time dilation equation becomes our relativistic constant times the proper time, or the time within that inertial reference frame, is going to equal what we know as the relativistic time. And here in the chart on the right, you can see a handful of examples of what gamma would equal based on the speed, the velocity v. And notice the velocity is given as fractions of the speed of light. Here we have 1/100th the speed of light, 1/10th the speed of light, 1/2 the speed of light, 90% of the speed of light, and 99% of the speed of light. And you can see the different gamma values. So just to clarify here, the time interval in the frame where the two events occur, so within the inertial reference frame inside the clock, is known as the proper time. But the time observed in a different reference frame that is moving with respect to the first one is known as the relativistic time. So this introduces a really interesting paradox. So it's been proposed that space travel could take advantage of time dilation. So if an astronaut's speed is close enough to the speed of light, a trip of 100 years could appear to this astronaut as having been much shorter. Let's do a quick example of this, just to see. So we want to know how much time would happen on Earth if a person travels out in space for 100 years. So your proper time is 100 years. And let's say that he is going at a speed of 0.99 times the speed of light. Okay. So let me rewrite this here. We know that the relativistic time is the relativistic constant times the proper time. Well, 0.99 times the speed of light would be 1 over square root of 1 minus v, 0.99 times the speed of light, and that has to be squared, and that has to be divided by c squared, that's our gamma constant, times 100 years. Well, if we come back here and look at our chart, 0.99c is equal to 7.1. You could put this in your calculator too. It's probably easier. To be honest, I never look at the table. In fact, I've already forgotten what that value was. 7.1, there it is. I just calculated it. So 7.1 times 100 years, it has actually been 710 years. So while the astronaut has only traveled for 100 years, on Earth, 710 years has passed by. Well, that is weird. So the astronaut would then return to Earth after being away for a few years. In this case, we said 100, but you could have easily made it 10. If he had been gone for 10 years, he would have found that 71 years had passed on the Earth. If he's even closer to the speed of light, being gone for just 2 years, hundreds of years would have passed on the Earth. Now you can imagine how weird this would be if you had a set of twins and one of the twins was the one that traveled for 100 years and the other one stayed at Earth. So one's only aged 10 years or 100 years, while the other twin has aged 71 or 710 years. We'll stick with these numbers. While one twin aged 100 years, the other one has aged 710 years. Yeah, weird. And so this has often been considered to be called the twin paradox. The twin paradox. So this brings up a really interesting question. If any inertial reference frame is just as good as any other, why doesn't the astronaut age faster than the Earth, which is traveling away from him? So let me see if I can word that in a better way. Here on the Earth, the astronaut is the one that's traveling 0.99 times the speed of light. And so while only 100 years has passed for him, 710 years have passed for us. Well, from the point of view of the astronaut, the Earth is what's moving at 0.99 times the speed of light. Why isn't it the Earth that only passes 100 years and the astronaut 710 years? So why isn't it the other way around? Well, the solution to this paradox is that the astronaut's reference frame has not been continually inertial. He has to accelerate 2.99 times the speed of light and then slow down. So because he's the one who has a changing reference frame, it has to be done from the reference frame of the Earth. An interesting phenomenon, really weird, and yet we have actually seen it happen. Here's an interesting observation, interesting example of where we've seen this. You've heard of the Hadron Collider in Europe, where you have one end of a great big huge long tube that is in, oh, I don't remember exactly where it is, Belgium, somewhere around there. And the other end of a tube is in Italy. Well, what they did is they synchronized the two clocks on both ends, and then they had a particle, and they sped it through and timed how long it took to go from Belgium to Italy. Well, guess what? Based on their time, this particle was actually moving faster than the speed of light, which we know is not possible. What happened? Well, it turns out that here they timed two clocks. So here are my clocks, both timed at 3 o'clock p.m. They timed the two clocks so that they were completely synchronous. But then they had to take this second clock and transport it all the way over here so that it was in Italy. And while it did that, it had to go at some velocity v. So, and because of that, while this clock may be reading, oh, let's say 5 o'clock now, this clock, because it had been traveling at a velocity v, time passed at a slower rate, and so it might be a few minutes before 5 o'clock. So, whereas they were both at 3 p.m. here, now this says 5 o'clock p.m. This might say 4:58 p.m. The clocks were no longer synchronous. Why? Because that clock that went to Italy was moving at a velocity v, we had to take into account relativistic effects. And so that clock was now fast. It was now behind. And because of that, it recorded an arrival time earlier than it should have. So we have actually seen evidence of these relativistic time dilations that we did not expect.